Okay. So now I have to imagine there is 600 people here in the hall. So thank you very much for coming to my presentation. And the topic today is called ES-TRNG. I would like to introduce our new TRNG's work, and we have groups there. And the new TRNG is based on the edge sampling, and you can see that there's a ring oscillator, and we're trying to locate the edge. And the sample result is encoded as random numbers here. And I'm pretty sure most of you have seen these pictures, architectures many times. It's the generic TRNG architectures. It consists of everything for the TRNG. It consists of the entropy cells, the digitalization, the post-processing applications, downline test. And for today's talk, ES-TRNG covers the topic of the digital noise cells. And for the other works, like the downline test for the ES-TRNG, there will be the future work. And for ES-TRNG, it's the timing jitter-based TRNG. And it has a compact implementation, and it has a relative reasonable throughput, and the security analysis of the ES-TRNG is supported by a stochastic model, which is very important. Why we need stochastic model to support the security analysis of the TRNG? And the reason is it's coming.
Talking too fast. Slides cannot follow.
Okay, I will slow it down and wait for the slides. Yeah. Because for a lot of cryptographic applications, we need a secure TRNG to generate the keys, to generate the initialization vectors, to generate the masks for the sectional resistant designs. But the security of a TRNG depends on its unpredictability. And what's the meaning of unpredictability? It means that with all the effort, an attacker cannot get an output of the TRNG. But this unpredictability cannot be measured by statistical tests, like the NIST 822 test, and the Bohan test, the Phipps test. But this unpredictability can be estimated by using a stochastic model, which is required by AS31, and maybe it is required by the NIST 890B, and maybe for some other standards in the future. And now let's have a look at the timing jitter-based TRNG. So this is a ring oscillator, and if it is noise-free, all the transitions of the signals in the ring oscillator is purely deterministic. We know where it will happen, when it will happen, but in the real case, there will be always noise in the ring oscillators. And in that case, the edge of the transitions will be unpredictable. And I would like to note that a random bit is only generated when people is trying to measure the position of the edge. For example, this is the simplest timing jitter-based TRNG. It's called elementary TRNG. There is a free running oscillator, and the signal is sampled using a D flip-flop. And how the random bit is generated? The random bit is generated when we're using a signal to sample the signals in the oscillator. So if the rising edge of the sampling frequency is after the closest rising edge of the signal in the ring oscillator, the result is encoded as 0. But if it's before, the result is encoded as 1. And in a more general concept is that this is the signal, and if the relative phase of the sampling is because of the noise, it's following a constant distributions, and if it's the mean value of that relative sampling phase is at exactly the rising edge, we will have the ideal case, that's the probability which will be encoded as 0 and equal to the probability that will be encoded as 1. But for the worst case, it's like this. And it needs to accumulate a lot of jitter to have an unbiased output. But the problem is that the timing jitter in the ring oscillator accumulates very slowly, which means that we cannot have a very fast elementary TRNG. And we believe the solution should be increasing the sampling resolution. And here, I want to use several existing examples for timing jitter-based TRNGs to show the idea. Here is the multiple ring oscillator-based TRNG. It consists of multiple oscillators here, and we use another oscillator to sample the output of those oscillators. And in the very beginning, assumptions of the mural multiple oscillator-based TRNG, it assumes that all the oscillators are independent between each other, and if n is sufficiently large, so all the edges of the oscillators are uniformly distributed. So if the n is large enough, at least one edge will be very close to the rising edge of the sampling signal. And which means that if we have enough oscillators here, we just need to accumulate the jitter a little bit. And conceptually, it is not said in the paper, but conceptually, the mural TRNG is actually corresponding to sample a oscillator with a resolution around T over N, and T is the average period of those oscillators. And another technique was used for timing jitter-based TRNG. It's called coherent sampling. As you can see, that there is an example with two different clock signals, clock 1 and clock 2, and they can be generated either using the PIL or free-running oscillators. And for the case in the slides, the period ratio between clock 1 and clock 2 is 5/7. And as you can see, if we are assuming that if we are using the clock 2 to sample the clock 1, actually we are sampling the clock 1 at a different phase of the clock 1. So that's called coherent sampling. So for the case here, it actually corresponding to sampling the oscillator 1, clock 1, with a resolution of T clock 1 divided by 5. And what else we can do to increase the sampling resolution? Maybe we can sample the oscillator at a higher frequency by increasing the sampling frequency. But the highest sampling frequency is limited by technologies, by platforms, by systems, by all kinds of things. And for the Xilinx platform we are using, the maximum sampling frequency you can achieve is around 300 megahertz and 400 megahertz. But can we do something better? We published the idea of the DC-TRNG at the DAC 2015, and we use TD-SIG, time-to-digital converters, to sample the signals. So as you can see that there is a free-running oscillator, and the signals propagate through a tap delay chain. And if we take the snapshot, the signals of the propagate through the tap delay chain will be stored. And for the Xilinx platform we are using, the average step of the tap delay chain is around 17 picoseconds, which is corresponding to sample the free-running oscillator at a frequency around 60 gigahertz, which cannot be achieved by just sampling the signals on the FPGA. But here also comes the problem. The average period of this kind of free-running oscillator is around 2.2 nanoseconds. And we have to design the tap delay chain long enough to cover at least one half of the signal, to make sure there's always an edge in the delay chain. And if we do the simple math here, we divide by 2, divide by the average step, and divide by 4, because in Xilinx we have two tap delay stages together to form one carry 4, which means that we have to stack around 17 slices together, and to provide some safety margin to accommodate the temperature variance and this kind of things, we use 20 slices together, which is not that much, but it's also not small. So we were thinking, what can we do to improve the implementation of the DC-TRNG? So that's why we come to the ES-TRNG. What we are doing is, we just delete all the rest carry chains and only use one carry 4 to sample the signals in the free-running oscillator. But now, the carry chain, the tap delay chain, is not long enough to cover the half period of the signals. And in order to solve the problem, we come up with two different techniques. But before that, let's have a look at the architecture of the ES-TRNG. So we have the free-running oscillator 1 as the noise source, which the jitter accumulates there, and the signals it propagates through two stages delay chains. And we use another oscillator to generate the sampling signals, and we use that to trigger the samples here, and the result is encoded by using a bit extractor. And the truth table here is indicate how we encode the result, and we only encode the result if there is an edge being captured by the delay chain. And to explain the idea, we can check this slice. So if we take the sample now, this is the signal propagated through the tap delay chain, and if we take the sample now, the sample result will be 111, which according to the truth table, the result will be not be encoded, so no result. But if we let the signals propagate, and if we take the samples right here, when the edge happens at the first stages, and for example, in the case here is the falling edge, the sample result is 110, and according to the truth table, the result is encoded as 1. Of course, if the edge is in the middle of the second stages, the result is 100, and the encoded result is 0. And similar things apply to the rising edge of the signals, and this is called variable precision phase encoding. And if we zoom out and check the whole stories here, we only encode the phase which is close to the edge with very high precision. And for the rest of the phase, we just ignore it. And this is conceptual pictures here. And the ratio here is just to illustrate the idea, but in the real case, the high precision region is very narrow compared to the low precision region. And if we encoded the whole part here as 1 and the whole part here as 0, it's actually equal to elementary TRNG. But as you can see that if the region here is very small, which means that if we take a sample, in most of the case, we will not capture an edge, which means that we have to take several samples until we hit the edge. So that's why we come up with the second technique. We call it repetitive sampling. And here explains the timetable here. And first, we let the free running oscillator accumulate the jitter for TA time. And after that, we enable the second oscillator, starts to sample the TRNG. And we sample it many times, we hit it once, and all sample result is 0, 0, 0, and 0, 0, 0, until we capture an edge. And the result is encoded to 0, and then we trigger the value signals. That's the entire loop to sample one data, 1 bit, random bit. And we know that there's dependency between each samples here. And this dependency is taken into account when we're building the stochastic model of the ES-TRNG. And how we implement the ES-TRNG of the Xilinx FPGA. So we implement the oscillator 1 with 1 lookup tables, oscillator 2 with 3 lookup tables, and we implement the tap delay chain using the carry forward primitives, and the result is stored in the flip-flops. And in total, we use 5 D flip-flops, 1 carry forward, and 10 lookup tables to implement ES-TRNG on Xilinx. As you can see, it's very compact. And but in order to use the stochastic model of the ES-TRNG, we have to measure the platform. What's the intrinsic physical parameters of the FPGA part we are using? So we measure the period of the oscillator 1, oscillator 2, and we measure the steps of the tap delay chain. And we measure the timing jitter of the oscillator and also the duty cycle. They are all used as input of our stochastic model. And once we fit the input to our stochastic model, we also play with the different design parameters. Here is the result, the estimated entropy of our ES-TRNG under different design parameters. And as you can see that as increasing of the jitter accumulation time, the minimal amount of the mean entropy is increasing as well. And as the next step, we want to optimize the throughput of the ES-TRNG. So we go through all possible design parameters of the ES-TRNG, and we found the optimal throughput here is around 1.15 microbit per second. If we use the jitter accumulation time 250 nanosecond, and with this scheme, we guarantee the output entropy is always more than 0.97. Here comes to the conclusion. ES-TRNG has a compact hardware on both Xilinx FPGA and the Intel FPGA. It has a relative high throughput, more than 1 megabit per second, and its security is supported by a stochastic model. And for the sake of, for the lack of time, I didn't present the detail of the stochastic model. But if you're interested in, you can go and check our paper, or maybe go to that web link. And that's all my talk. Thank you very much.
Questions for Bohan?
Why isn't the stochastic model in the ePrint version of the paper?
Why the stochastic model is what?
So you point to your website for the paper. Why didn't you put it on ePrint?
ePrint.
Yeah.
Yeah, ePrint is the paper. We didn't upload the paper to the ePrint. Yeah, it's not linked to the ePrint. Yeah, but we only have 20 minutes, so we cannot provide the details of the stochastic model.
Yeah.
No, I think the paper is on ePrint, right?
But it is, why not put the ePrint then?
Just automatically puts them on
People
ePrint.
more like to fight that.
But he says that the stochastic model is not in that version. So there's a version on ePrint that does not have the stochastic
We don't have a
model.
version on the ePrint.
You don't have a version of ePrint at all.
You're saying he's lying?
Does
No, I said, why not put the paper on ePrint? People are more likely to find it.
Yeah.
ePrint is better than your homepage.
Yeah,
But normally chess should do that automatically.
I thought that one. I thought
Final
that one
versions
was
get
the
automatically
No, I
should
didn't
get,
do
sorry.
versions.
I know.
Should get.
Yeah, and also the reason we
Maybe that was when it was chess and now it's T-chess.
Yes, exactly. Yeah.
and the reason we want to put a link here because we're probably in the future we also want to open source our code and some other materials rather than the contents in the papers. So that's why we want to provide this link.
Yeah, but he actually has a point. Eh? When you're gone in 3 months or 4 months, what happens to your homepage?
Yeah.
ePrint's permanent forever, and it will always stay there. Put it on ePrint.
Okay.
Yeah.
Data on ePrint.
Yeah.
Well, at least the paper.
At least the paper.
At least the paper, yeah.
Data, GitHub, COSIC GitHub.
Yeah, GitHub as well. We can use that. Any other questions?
Okay. So I'm assuming you ran statistical tests on these outputs to check to see how well they agree with your entropy estimates?
Yes, yes. As you can see that we have this page here and here. Yeah, and we try different parameters here and we apply the NIST 890B to test the Python code, and the estimated entropy from the Python code is always larger than the estimated entropy from our stochastic model. So which makes
That's what you'd expect, I think.
Yeah.
Right? Okay, I hadn't understood that. So I guess I thought that this was just doing that this diagram was just doing your simulations and your estimates. I didn't realize that you're comparing.
Yes,
Yeah.
and actually there's another information which I didn't see during the presentation is that because of the existence of other type of noise rather than the white noise, it's very difficult to estimate what's the initial phase when we start to sample the oscillator. So that's why we exhausted all the possible initial phase from 0 to 1 to check the global minimum entropy. So we just use the global minimum as the most conservative estimation estimation.
So I guess now I'm trying to understand your diagram here.
Yeah.
So maybe this is something you could clarify in your presentation.
Yes.
So the measurement here is you're changing your parameters of your model.
Yes.
And then are you running a simulation of that to get bits and then running statistical tests on those bits? Or are you building hardware and changing the model inside the hardware?
So what the parameters we are changing here is the design parameter. So for example, we cannot change the jitter strength on the FPGA, but what we are changing here is the jitter accumulation time. For example, here we accumulate only 5 system clock cycles, which is around 50 nanoseconds to the 200 nanoseconds here, 200 nanoseconds here. And because we accumulate more jitters and the result is better, this result here are based on our stochastic model, which is implemented in MATLAB. But later the result here we verify the results using our real hardware. For example, we let the hardware accumulate to that amount of time and then measure the result and check the entropy afterwards.
And these, the dotted lines here from your actual hardware, these are the estimates from your stochastic model?
Yes, yeah, so that's the result from stochastic model.
For Shannon entropy and min entropy?
Yes, this is the theoretical limitations for the Shannon entropy from our stochastic model, and this is the mean entropy. And because our target is to guarantee the output is always have a entropy more than 0.997 Shannon entropy, which is required by the AI-31 test.
Yes.
So that's why at the beginning, so if we accumulate a little bit jitter, we need to apply many stages of the post-processing to reach that entropy level. But if we accumulate a little bit longer for the jitter, we only need small stages, like 3-4 stages for the post-processing to reach that entropy level. So that's why we have a lot of different segments here. And here represents that we don't need the post-processing anymore, so just the raw bit.
Right. And did you, for the actual hardware outputs, did you run, I'm assuming you ran those through the statistical tests as well?
Yes.
And that's where you got lower, so that the statistical tests were always estimating more entropy than your model was?
Yes, the result is also in the paper inside the table.
Okay. Right. And maybe you could make that a little more clear when you give the presentation, although I know you don't have very much time, so you can't go over a lot of
Yeah,
these.
I will try to improve this as a previous test. Thank you.
All right. Thanks again.
Thank you.